Hello viewers, you must be getting satisfied, you must be sure, and I am confident, and we can agree to one thing, that mathematics is gradually getting to its maturity. Most of the things have been done, whatever is left out to be done is again very interesting. We had come to a position where we are dealing with partial differential equations. We left last time where we were doing linear differential equation of the first order. We'll continue it, and then we will come to nonlinear partial differential equations of the first order. So we must settle down to agree one thing, that we are noticing, we are witnessing the attainment of the maturity of mathematics, rather advanced mathematics, from special function to series solution to beta and gamma function to Legendre polynomials to Bessel's function, their solutions, and now we are continuing with linear differential equation of the first order. The non-homogeneous will again interest you, though again I must confess that we will not be dealing with it very detailed, but we will be covering almost, which is easily understood, comprehensible, and things becomes easy for us to apply them. To begin with, as I have told you, that in this part of lecture intend to continue from where we partially completed the linear partially and all, in other words, is a partial differential equation of the first order. And then we will begin with a very important thing, Lagrange's solution of linear equation. If you recall, we did something which we call as Legendre's equation, and now we will be going to Lagrange's solution of linear equations. I will refer to the previous lecture as well, as you can see here. We have in the previous lecture seen the equivalence of the equation 32 and 33. We have also noticed that the general solution of 33 is obtained by finding two independent integrals of the equation. You can see it looking like something as a ratio, dx upon p, dy upon q, dz upon r. P, q and r carries the same meaning as we have decided earlier also. We are marking it as equation 1. Then if u is equal to a and v is equal to b are two independent integrals of 1, then we write this thing, that a function of u and v will be equal to 0, or in other words we can say that v is a function of u. Fair. This is the general solution of this equation, p partial du dx, q partial derivative of u with respect to y, and then plus r partial derivative of du with respect to z, coefficient being r, all equated to 0. That is the equation number 2. That is the general integral. This general integral is the complete solution of it, will be given by pp plus q, q is equal to r. We have marked it as equation 3. Equation 1 are called Lagrange's auxiliary equation. This name is very, very important, prominent, and we must understand that. I am talking about the equation 1 where we have studied dx upon p equal to dy upon q is equal to dz upon r. I am referring to that equation. This equation 1 are called Lagrange's auxiliary equations. The plural equations is given because you can pair any two out of the 3. For example, I will be getting dx upon p paired with dy upon q. The second pair will be dy upon q equal to dz upon capital R, or you can even go with dx upon p equal to dz upon r. So these 3 combination, or even you can go for 4 combinations, will be called as Lagrange's auxiliary equations. The curves of intersection of the surface u is equal to a and u is equal to b are called Lagrangian lines intersection of these two surfaces, u is equal to a and u is equal to b. Verifications of Lagrange's solution. This part is very important. We would like to see that this part gives you a meaning as how Lagrange's solution is obtained, and whether Lagrange's solution satisfies the linear differential equation of the first order is the main objective that we want to do, the main objective that for which we are running this whole part of analysis. We suppose we begin by like this, that u is equal to a and v is equal to b are two independent integrals of the equations dx upon p equal to dy upon q is equal to dz upon r. The same thing, we are coming from equation 1 carried over. We differentiate. So, we write differentiating. This differentiation is again a total differential that we have studied in the portion of our elementary partial differentiation, from where I am borrowing this particular result 7 and 8. So, we have differentiated 4 and 5, we obtain. You can see all has a coefficient something like this, du upon dx, total differential dx, du dy, total differential dy, and then du dz equals to 0. And the second that we will be obtaining with respect to v is dv upon dx, dx, dv dy, dy, total differential dy, and the last is partial dv with respect to z. These two equations 7 and 8 are simultaneous equations that you can see line written below. Solving simultaneous equations 7 and 8. What we are going to have from this is this one. We solve it like this, the same simultaneous equation which you used to solve in elementary classes as schoolwork or classwork. This is dx upon dy upon dz upon. These are the three terms, something like ax plus by plus c, and then again a dash x plus b dash y plus d, that which we have done in elementary classes. We write x upon something, we write y upon something, we write constant upon something. So, we make what we call as a cross multiplication, if you recall, with a negative sign in between, the same thing that we are doing here. So, we get dx upon du dy, dv dz minus du dz dv dy, similarly for dy and similarly for dz. I hope this particular equation 9, the method of obtaining equation 9 is made clear to you by giving that example which we have done as simultaneous equation in 3 variables, simultaneous equation in 2 variables. We do the same thing. After having obtained this equation 9, we compare 6 and 9, 6 that we have written, that is dx upon p, dy upon q and equal to dz upon r. We are comparing these two, the previous equation number 9 and now what we have, the equation 6. By comparison, it is very obvious that equation 10 can be obtained. Instead of dx, dy, dz that we had in numerator, now it will be replaced by pqr because the comparison is so simple to write here. Then look at this, partial differential equation is obtained by the elimination of arbitrary function this equal to 0. I wish that I ask you to recall what we have done in the previous lecture. There are two methods of solving the Lagrange's equation, or in other words, when we have started the last lecture, we have studied what we call as there are two methods of solving or forming a differential equation or deriving a differential equation, partial differential equation. The first is by eliminating arbitrary constants, do you recall? That is function of x, y, z and then a and b. We removed a and b. The second method that we imposed and we tried to understand in the last lecture was by elimination of the arbitrary functions. We are applying that thing. In that case, if you recall, we had the equation as function of x, comma y, comma z, comma u, comma v. We have the same thing here. This is a function of u v is equal to 0 and we want to use the method of elimination of the arbitrary function, and then 10 gives these things, small p, small q, and this equal to this thing which will be called as capital R. This P and this Q is nothing but the same meaning. First order partial derivative. dz upon dx was denoted by P in our previous lecture. dz dy was denoted by Q, if you remember. And on the right hand side, after taking common and after simplification, you get this result. So, we landed at equation 11. We proceed further. But having obtained 11, the whole theory concludes now. We say that this justifies that the function of u and v is equal to 0 is the general solution of the equation 11, and hence the Lagrange's solution is justified or verified or it is proved. The Lagrange's equation, which we have studied earlier, that is dx upon p is equal to dy upon q is equal to dz upon r. So, everything is very simplified, and I am confident that we could understand what we mean by very simple method, simple comparison, simple adjustments and few eliminations, and then we have applied that elimination method of arbitrary function. We will notice a few examples which I tried for you, and these examples will make you to understand that what we have meant earlier in the preceding couple of pages that we started lecture this time. So, today's lecture started with this, simplified everything, we obtained the Lagrange's solution and we have reached its verification. Having attained the verification, or in other words justification, we solve the first, and that first solution or the first example is like this. The equation is given as Pz minus Qz is equal to z square plus x plus y whole square. All the functions are in x, y, z. That is noticeable. So, the given equation, as you can see, is given as Pp equal to Qq is equal to r. If you recall this definition, the capital P is a function of x, y, capital Q is also a function of x, y and z, and r too is a function of the x, y and z. We compare this from the earlier or from the previous lecture, and we write that here P is equal to, capital P is equal to z, capital Q is equal to minus z. Look into the equation which is given, and r the right hand side, that is z square plus x plus y whole square. Everything is classified. We proceed with everything in our hand. That auxiliary equation which we have written, that is referred to as equation 6, is written like this: dx upon p, for p we write z, dy upon q, for q we write minus z, then equal to dz upon r, for r we write the right hand side of the equation 11, which is this, z square x plus y whole square. Okay, everything is done now. The first and the second term that we make, as I have told you, we can pair any two, first and second, second and third, third and 1. So, I am taking first and the second term, meaning thereby I am taking dx upon z and dy upon minus z. Since it is a ratio, the third term is very easy to understand. If a upon b is equal to c upon d, we write each one is equal to a plus b upon c plus d. Same thing I am writing here. The numerator adds up to give us dx plus dy, and in the denominator we have z minus z results into 0. We solve it and we write dx plus dy is equal to 0. Very simple. If I combine the second with the third, the first with the third, each time I will be getting dx plus dy is equal to 0. Total differential. I integrate, so integration becomes very easy. For dx I will be writing x, for dy I will be writing y, and a obviously is a constant of integration that frames this simple equation. We call it 13, and 13 is this equation. Very simple to understand. When we integrate, you get all that. So simple. A is a constant of integration that we say. We move further. According to the theory, the basics of it, now I take the first and the third term. First and third term is this, dx upon z was written there, dz upon z square plus x plus y whole square. So, in place of this I will be writing a square, that is the only thing obtained from using the equation 13 in the previous terminology. I integrate again. So, what happens like this? Integrating it, I will be getting 2 times integral dx plus 2 times integral z dz upon z square plus a square. We get 2x the integral, dx is the total differential, its integration is x, constant again is b, what we call as constant of integration, and it will be log of z square plus a square. Do you recall that how it is interesting to make it this right hand side? Why after all this 2 comes? 2 comes with a notion that z square plus a square is the, if I differentiate this, it will give you 2z. So, what I did is that I multiplied and divided by 2, and so I applied the formula that if I want to integrate certain integrand where the function is in numerator and its differential is in denominator, then the answer given to it is log of the denominator, same thing. And now I believe you could catch up with this, is easy thing to understand this one, which I wanted to make it very easy for you, this right hand side. If you look into here, that formula comes in our mind, simple but essential to learn. Last step that makes the equation 14 is easy. Simply we have rearranged the terms and b is brought on one side, the constant of integration. And so, the general integral, I have told you earlier as well, this general integral means the solution of the given partial differential equation. Anywhere you write the integral is this, we will mean that we are heading for the final conclusion of that problem, means we have solved, obtained the solution, and obtaining a solution is called as the general solution or integration. Therefore, we write general integral is given as this. Second question that we undertake is x is dz dx, y dz dy plus t dz dx equal to all that in the right hand side. Solution begins. This auxiliary equation is also called as subsidiary equation, Lagrange's, I mean the same nomenclature. So, unless otherwise something serious is talked about, we should not get confused. Subsidiary carries the same meaning as auxiliary equation. Equation becomes dx upon x, dy upon y and dt upon t, and the fourth, that is dz upon az plus xy upon t. This is Lagrange's equation, that equation which we have started right at the beginning. Again the same ratio, and so we consider first and the second terms and integrate. This time I did not write the all terms in between, but you can understand first and the second term. You will be getting dx upon x, dy upon y. We integrate, you get log of x equal to log of y equal to log of c1 is a constant. Use the logarithmic formulas, that is log of m upon n or log of m to the power n or log of m into n. So, everything, and that gives you y is equal to c1x, equation 17 that we arrive at. First and the third term now. First and the third term applies the same thing. C2 is a new constant of integration and you get t is equal to C2x. Simple to understand, similar as C1 was given. Now take the first and the fourth term, because there were 4 terms, so we will have to operate this also. Had there been 3 terms, we would have taken first and second, second and third, or first and third. But now since it is the 4th term, so we will be having this first and 4th term. From the given equation, we have dx upon x is equal to dz upon all these, and then we will be having this written as dz upon dx minus this c1 upon c2, which is given as equation 19. It is very important, note that 19 is a linear differential equation, very ordinary of the first order and first degree. I have written that equation. To make you recall some preceding years where you have studied probably this, dy upon dx plus py is equal to q. It's a very well known equation, and we have been taught that we must find an integrating factor of it. I will tell you briefly what integrating factor is. You see, integrating factor is something what I would say you, something like without this the solution will be impossible. So, we find something will be impossible means we will not be able to integrate the variables, or we will not be able to integrate the whole equation. And as I have told you, without integration you cannot get a solution. So, to make it possible for integration of the given equation, we add something. In English language we call it a helping verb. Similarly, we call it an integrating factor. Give this, make a whole sentence in English, make a whole sentence in mathematics. That means we are approaching to the solution of the equation. Integrating factor, the standard form that we have is e to the power integral p dx. P is this one, pp is equal to q. So, if is the notation for integrating factor of 19 is obviously, the 19 in the preceding page is obviously e to the power minus a upon x dx. So, it becomes e to the power minus a log of x, that is all. And so, log of x is written as, since it is minus, we will be writing it as 1 upon x to the power a. This needs no advanced mathematics. So, 20 is a very simple result. So, that the solution of 19 now is given is this, C3 is another a constant, and the general integral in turn is given in the shape of equation 21. That is the final solution that we obtain of the example that we have undertaken. That concludes the linear differential equation of the first order completed with 2 or 3 examples. This is enough that we can understand. The only thing is to be understood, as you have seen, is the Lagrangian auxiliary or subsidiary equation written as dx upon p is equal to dy upon q is equal to dz upon r. Pairing them, take 2 pairs, solve it, get a first constant of integration, then take another pair, go for its solution, simple integration, give you the second constant of integration, and write the solution as function of the first constant and the second constant. That is all. We need not to undergo much thinking, we need not to undergo more complications, simple results. We come to this important thing which we call as nonlinear partial differential equation. I tried to give you 2 lines that why we call it a nonlinear, why not a linear. The reason is this. Here we consider equation in which p and q occur other than the first degree. Other than the first degree. If it is in first degree, which we have seen just now, we call it linear. For example, in coordinate geometry, we write ax plus by plus c is equal to 0 represents a straight line, and we are taught that if x has a power 1, y has a degree or power 1, we call it a linear, and any straight line which is linear represents this ax plus by plus c is equal to 0. Similarly here, p and q will have the degree 1 only, and then we used to call it first degree. But now this all becomes not a linear, so we call it a nonlinear, and therefore we call that if it is other than the first degree, then we call them a nonlinear equation. Very simple. More general method though is called Charpit's method. There is a method called as Charpit's method. We restrict the details to 4 standard forms only. This does not include in our course contents. Charpit method is a very general method, but nonetheless, without Charpit's method, we will be discussing 4 methods, 4 standard forms, standard 1, standard 2, standard 3, standard 4. They are specific, easy to solve, and once you will have to notice the given equation is in which standard, since we have all the categories down there. The first warning is this: sometimes change of variables can be employed to bring a given equation to a suitable standard form. It may not happen that every time you are given standard 1, standard 2, standard 3 and standard 4 that we are going to study now, but some change of variables, suitable change of variables that we are to observe, we are to find, we are to study by practice, will make them to look into any of these standard in number 4. So, standard 1 is equation of the form f p q is equal to 0. In words, what we write, that the given equation will only contain p and q, not x, neither y. Second standard, we will be having only equations of the form z p q is equal to 0, no x, no y. Standard 3, we will have on one side function of x and p, the other side on the right hand side, as you can see, it will be a function of y and q. P and q has the same meaning, x and y are two variables. Standard 4 is a little lengthy, but very simple. It is written as z is equal to px plus qy and a function of p and q. All jumbled together with a positive sign gives you a shape in standard 4. So, standard 1, standard 2, standard 3 and standard 4, these are the 4 which we are interested in giving a little brief idea as to how to solve it, and we start with the concepts of this standard 1. As I have told you, these equations in which x, y and z do not occur explicitly, they do not. Complete integral, which we will denote by Ci, is given by z is equal to ax plus by plus c, where a and b are connected by this relation marked as 23, where p, as you know, is dz upon dx is equal to a, q dz upon dy partial derivative is equal to b. And then finally, when we substitute it in equation 3, the form PQ is obtained. Few examples will make it still simpler, easy. Standard second is, let us assume that the tentative solution, it may not be the complete solution yet, but tentative, what we assume as, is given by z is equal to function of x plus ay, where x is an arbitrary constant and therefore z is equal to function of a capital X, where x is represented as ay plus x, that is equation 26. Then very simple, p and q can be defined. We have said it involves the total differential, it involves the partial differential, and 27 and 28 you can see that it is represented as p is given as dz upon capital Dx and the other one is given as small a coefficient and then dz upon this. Therefore, the equations becomes function of z, p and q equated to 0. And this all reduces to equation 29, which obviously is an ordinary differential equation of the first order. Obviously, first order means dz upon dx has a power 1 and therefore, we call it a order. Integrate to get the complete integral, simple. We summarize now this lecture. We have started with Lagrange's solution of linear equations for which the general solutions are discussed. Once again, everything briefly has been told to you during the lecture, during the time of lecture that I delivered, and you were listening to very patiently. But one thing is very sure, you must have enjoyed the easiness of mathematics, the simplicity of mathematics, and how fundamental that we can treat any bigger problem that you have noticed. We have even borrowed the very elementary knowledge of mathematics that probably we have studied in elementary classes in schools. In schools, when we started algebra, when we started trigonometry, when we started calculus, or when we started simultaneous equations, everything can be seen here. That is the beauty of mathematics. The beauty of mathematics is not solving problems only, not getting theories only. The only thing is that we should be able to recall what we have done. We should be able to give meaning and attach a meaning to what has been taught to us in the previous classes, and how they can be very useful to us now at an advanced stage like what we are in. And so, we discussed all the fundamental theory. Then we came to nonlinear and we discussed 3 standards here, the standard 1, standard 2, standard 3, standard 4. Namely, they have been taken very much tender care giving you the shape of those equations. Shape means, for example, the first standard did not have any x, y or z, it is only pq, that is all. Function of pq is equal to 0. What now we will be having is a little progress from where we have left. We will be discussing more standard because we could not complete all the standards here. So, what we want to do is to show you how the other standards looks beautiful, like the one that we observe here, and we see as how all these standards mixed together one after the other gives you an elegant solution thinking of the recent and advanced mathematics. Thank you for all that attention you have paid.